Section 8.2. Well, we talked about in Section 1 about graphing as a way of solving or finding solutions to systems. We're going to go through two different methods in this section. One is called substitution method and the elimination method. The substitution method is a non-graphical method, which is more accurate, definitely. And that's what they say is they are superior, because we're going to find the exact numbers that will work in both of those. Well, let's just look at this example to start with, and they'll show graphs, because mostly, like I said before, is graphing is just a great way to give you a visual of what's going on with these things, especially with linear equations. Well, example 1, they want us to solve this system. We have these two equations, x plus y equals 4 and x equals y plus 1. And the solution would be, using a substitution method, is if we solve one of the equations for a certain variable. In fact, they've already done this really in equation number 2, and the reason they numbered these is for reference here. It says that x and x plus 1 are the same number, or they're equal to each other, right? So we can substitute that into the other equation, and that's what they do here, is x plus y equals 4. They replace the x with this part here in equation 2 for what x is equal to. So this represents x in the other equation, and then we end up with an equation with one variable. So we simplify this expression. We get 2y plus 1 equals 4. Add negative 1 to both sides, we get 2y equals 3. And then take 1/2 times both sides to solve this for y, and we get y equals 3/2. Well, that's one of the parts of this ordered pair that we're looking for, and this is going to represent the y value. So we can go back into one of the equations, and probably equation 2 would be easier, though you could use either one. X equals y plus 1. Well, we have a value for y, so let's substitute that in, and so we're trying to find out what x would be in this case where y is equal to 3/2. So we'd end up with x equals 5/2. So we end up with this ordered pair, 5/2 for x and 3/2 for y. Now, if we did all our math and algebra right, this ordered pair represents the common ordered pair that is a solution to both of these equations. And I can test that. I could go back into either one of these and see if those work in that case. So that's what they do. They check the equation x plus y equals 4, and they put in 5/2 and 3/2 respectively for the x and y, and they get 8/2, well, which is the same as 4. So that's true. That is a solution for this equation. And then they get 5/2 equals y plus 1, which is 3/2 plus 1, which ends up to be 5/2 equals 5/2. So this checks, or this ordered pair is a solution to the system. Example 2, they go through another case here where we have these two equations. Well, they're not pre-solved for one variable, so we choose one. So first we select an equation and solve for one variable. In this case, they took 2x plus y equals 6, and they solve for y, which is y equals 6 minus 2x, or you could write it as negative 2x plus 6. Then we proceed, as in example 1, by substituting. So this area right here, this 6 minus 2x, or negative 2x plus 6, represents y from this one here. Now be careful, you can't substitute it back into the same one that you solved for, so I have to use the equation 2 here in this case, which is 3x plus 4y equals 4. I substitute in this 6 minus 2x for y, so I have 4 times the quantity of that. Make sure you you know that you have a quantity symbol there. Use the distributive property to get rid of the parentheses, and then we can, if it's all addition, we can change order, right, and we can combine like terms, which is in this case, what they did is took a negative 24 and added it to both sides, and they end up with 3x minus 8x, which is negative 5x equals negative 20. Take a negative 1/5 times both sides, and you'll get a positive x equals positive 4. Well, that's one of my ordered pairs. I got a 4 for x. Well, to find out the other one, I go back to one of the, they say substitute 4 in the equation 1, 2, or 3. Well, 3 was I would caution that this would probably not be a good one to substitute back into, because we manipulated that. I would rather go back to the originals and do that, but they do that here, could save some time. And we end up putting 4 in for x. 6 minus 2 times 4, which is 6 minus 8, is a negative 2. So the ordered pair we think is a solution is 4, negative 2. Let's check it. Let's make sure that it works in both equations, and they substitute that in, and it does. So that is a solution for this system again. So the kind of one more step in there, you might have to solve for the equation before you can use this substitution. Solve for one variable, so you can use substitution method. Now example 3, let's look at this one, and they show us a graphical of this, you know, and we talked about this in section 1, that this is possible with linear equations, that they're parallel. In other words, there's no solution to this system. So let's look at what happens if we use substitution. We didn't graph this. We don't realize that these are parallel lines, though there are some things, if you remember, especially when they're both in the y-intercept, they say, hey, these have the same slope and different y-intercepts. The only way that can happen is they have to be parallel lines. But let's say you don't catch that. So they start using substitution. Well, they're both solved for y, so we could use either one, and I just take y from here, right, and I substitute it for y in equation 1, and I end up with this new equation right here of negative 3x minus 2 equals negative 3x plus 5. Well, when I solve this, I want to get the variables on one side of the equal sign. I add 3x to both sides, and I get 0 for both sides, and I end up with this situation where I have a constant equal to a different constant. In other words, and it's not true. This is never going to be true that negative 2 is equal to 5. When this occurs, that tells me there is no solution for this. So that's an indicator of this happening. Now we can do another method, and there's also another situation can happen when we have parallel lines, or basically multiple ones that are dependent. In other words, they lay right over the top of each other, and we end up, after we do this substitution method, we end up with something that is true, and they'll talk about it here when we review this. The next method is elimination method, and this is kind of like using this power, basically the addition principle or law that we've covered before. If A equals B, then A plus C equals B plus C. So to solve this equation, we have 2x minus 3y equals 0 and negative 4x plus 3y equals negative 1. Well, according to the equation 2, negative 4x plus 3y and negative 1 are the same number. And if we think about that, thus we can use the addition principle by adding this to one side of the equal sign, as long as we add what it's equal to on the other side of the equal sign, on the right side. And that's what they do. They show it as up and down addition here. Is, well, I'm going to add this is one side of this equation 1, and here's equation 2. Well, I'm going to add these two equations together, and I end up with a situation like this. And notice that when I do add these two together, I end up with an equation with one variable, because I end up with 0 times y, which is 0. Well, if I have one equation at the end of this elimination method, now I can solve for that one variable, okay? And then, so I end up solving for x, I get 1/2. We need to substitute the 1/2 in for x and solve for y. So we go back to one of the equations. There you go back to equation 1, they put 1/2 in for x, and you end up with this. We solve for y, and we get y is 1/3. And then we check to see if this is truly a solution, this ordered pair of 1/2, 1/3, right? So they substitute them in each equation, and yes, it makes both of those true. So that is truly a solution to the system. Now, so that's nice if the equations line up that way. Well, couldn't we use the multiplication principle that says that I can multiply both sides of an equation by the same number and I don't change what the solutions are, or I get an equivalent equation, to go back to some prior terminology? Well, what I want to do then is create a situation or create an equation so one of the variables will disappear when I use this elimination method. So here are the originals, and they take this equation 1 and they multiply it by -2. Why? To make this y, this 4y, turn into a -8y, because when I add that to 8y, I get 0. Okay? Now, why did they choose this one? It's nice if these things are multiples of each other, right? 8 is a multiple of 4, so I can easily take a whole number to multiply by, get these things to be common in a sense that they will be able to add together to 0. So they do this. Now I end up with an equation with just one variable. You get -13x plus 0 equals 26. So if you solve that, you get x equals 2. Then we go back to, in this case, equation 2 they put 2 in for x. Now I have an equation with one variable again, and I can solve and find out what y should be equal to. So we obtain this ordered pair of 2, 3, and we should check to see if that is a solution, and they just don't show the check on here. So I could put that back into both equations and do that. So they go through a couple of examples of finding good strategies to do this. In this case, they're actually multiplying both equations by a number. And what are they doing? You need to think about, what are they trying to do? Well, they decide that it'd be nice if we can get these x's to match up. Well, if I took 5 times 2x, I get 10x, and if I took -2 times 5x, I get a -10x. That's handy, right? Well, I could do the same things here to make these work too. I could use 7 times both sides, and I'd get 21y, and if I took -3, I'd get -21y, and you'd end up in a similar situation. So it's not about this is exactly how you have to do about it. You think about the strategy. What is elimination, and how can I use this? So how can I use the properties and laws of equations to make this fit, so I can use elimination? And you'll find that you'll like one or the other. A lot of times you get used to doing one, but be careful. You need to practice both methods. As we go in through the testing and the quizzes, it'll force you to use both methods or show that you understand both these methods. So make sure you practice both. So there's a situation where you had to do a little more manipulation with multiplication to get your elimination method to work. Well, here's a situation again where we have a line over a line. In other words, these are multiples of each other in a sense. If I use the elimination method, and I do this in this case, like they're going to say, well, I got -12y. If I can make this to be a 12y, I'd multiply by 4. So they multiplied this equation 1 by 4, and they get this. And then they add them together. well, this goes to 0 and this goes to 0 and this goes to 0. In other words, we get at the end of this a true statement. This is a true equation in a sense, but I lose my variable. In other words, no matter what I put in for the ordered pairs, if it's a solution to one of these, it'll be a solution to the other words. In other words, there's an infinity of solutions. Graphically, this is what it would look like, but that's the indicator that when we have a true statement with constants that come out of this, we can do that. And because there's an infinity of solutions again, the only way to represent this is with set notation, if not graphically like this, but set notation would be more accurate. And notice that in this case they do say that both ways to say the set notation is okay with either equation. I could say the sets such that the ordered pair xy, the set of ordered pair xy, such that this equation y, 3y minus 2x equals 6 is true. That's all the solutions. Or I could use the other equation, which is exactly the same infinity of ordered pairs. So they talk about these special cases. When we solve, if we obtain an identity such as 0 is equal to 0, or they're identical to each other, we say these equations are dependent. In other words, they're multiples of each other. And since the solution exists, it is consistent. In other words, it has solutions. There's just an infinity of them. Remember, the definition of consistent is that they have at least one solution or more than one solution. If you obtain a contradiction, or basically a false equation, or something that is not true, this system has no solution. The system is inconsistent. Okay, so they go through some more examples. Now, when I get into fractional stuff, remember when we talked about solving equations, one of the things that's easy to do, if you have a fractional equation, just if that was the only one you had, nice strategy is to clear the fractions by multiplying both sides by the common denominator or whatever. Now we have two different representations of fractions here. Here in the decimal system, this is 2/10 and this is 3/10 y, 2/10 x, and 3/10 y. And I kind of like thinking of it that way because it might give me a little more availability to understand what would be a good multiple to go by that would give me the method to use elimination. Well, there's different ways to do this. Here's what the book decides to do. First, they multiply both sides by 10, which clears the fractions, really. Then they multiplied both sides by 35. Why'd they come up with 35? Well, that's the LCM between 7 and 5, or least common multiple, right? And that clears the fractions. And if we multiply both sides by 10, and that's what they talk about, we get a common denominator. The problem now happens to be identical to example 6, and we can basically use elimination, and they just drop that out. So really what they're doing with this is just showing you how do I deal with these fractional stuff, because that can make that harder to deal with. So clear the fractions. Here's a summary of the two methods here. Solve a system with substitution. You can read through that, and solve a system using elimination. If you follow these steps, it'll take care of all that stuff. And then here also is connecting the concepts, which is nice. We went through the graphical method in section 1. It talks about its strength. It basically gives you a visual. That's a real strong thing in any kind of mathematics, if you can get a picture of it. Its weakness is that some systems can only approximate a solution can be found. Approximate solutions can be found graphically. You'll notice when they do graphical solutions, usually they end up laying the intersection points right on the grid. So it implies that it's very accurate, but it's not necessarily. When you get into fraction stuff, it is very hard to determine what that ordered pair may be. Well, substitution strength is you get exact solutions. You can use when a variable has a coefficient of 1, and it's very easy. That's probably an indicator, hey, I got x equals y plus 2, hey, or x equals 3x plus 2, right? I have an x, that's what they mean by coefficient of 1. In other words, it's very close, if not already been solved for one of the variables, which I can use to substitute in and use this method. Elimination also gives you doing that, well, excuse me, I kind of skip weaknesses. Introduces extensive computations with fractions when solving more complicated system solutions, and solutions are not displayed graphically. You're not really necessarily getting a picture of what's going on, which can be, especially when you're dealing with word problems, you can do a lot of work and come up with an ordered pair and then forget what that really means as far as the ordered pair. A lot of times graphically, we tend to get the picture and we understand that this graph represents what they're telling us in the word problem. Usually kind of fits together better. So be careful. Remember what the variables mean in word problems. Well, elimination, it talks about we can probably, when we get into fractional coefficients or numbers times the variables of fractions, we're probably going to look at elimination, and then its downfall is it isn't graphical in a sense too. And there you go. That's section 2. Good luck on the homework.